So then I think I'm sharing the screen. And if you're looking at the screen, let's see, today is Tuesday, May 23rd, 2023. This is session 19. We started this back in 2020. My name is Edwin German, and I'll be the moderator of this session. We have 4 outstanding presenters with us today. I mean, 3 of them are here. 1 will probably connect a little bit later. And let's just go to the very first presenter. So his name is Siva Prasad Omanakuttan, and he goes by Siva, I suspect. Is that true?
Yeah.
He's a graduate student in the group of Ivan Deutsch at the Center for Quantum Information and Control at the University of New Mexico. He's working on quantum error correction, quantum control, scrambling, and Rydberg physics. So the title of his presentation, as you can see on the screen, is Spin Squeezed. Oh, there's a U missing, correct?
Yeah, that's true.
Sorry, I'll add it. GKP codes for quantum error correction and atomic ensembles. So I'm going to stop sharing. I'm going to let Siva start his presentation.
I'll start sharing. Okay.
Yeah.
I hope everyone can see the screen and can hear me.
Yes, looks good. Yep.
Yeah.
Yes.
Okay. So I will. So thanks for this wonderful opportunity. My name is Shipp Prasad Omanakuttan. I'm a graduate student in the group of Ivan Deutsch at University of New Mexico. So today I'm going to talk about a work I have been doing. And it's out in archive with a research scientist in Los Alamos National Lab. And the title of my work, it's kind of big. It's Spin Skews GKP codes for quantum error correction in atomic ensembles. So we can dive into the talk. So first of all, we can start from the very basic, like think about the idea of qubits. So we have the qubits, which are like the standard paradigm we think about quantum information. So the qubits are basically a 2-level system. So it's very related to the bits, which are 2 bits. So in the case of bits, we have the 0 and 1. So the difference with the qubit is that for a qubit, we can have a state, which is a linear combination of this 0 and 1, and this alpha and beta can be a complex number. That's a qubit state. Now, when you think about a fault-tolerant quantum computation, so what is meant by fault-tolerant quantum computation is that this is also the idea from classical computation is we need to do computation even in presence of errors. That's the idea of fault-tolerant computation. So one standard way we think about implementing them is actually having a logical qubit being a collection of many qubits. So at the logical level, a qubit is like a collection of many number of qubits. That's a logical qubit, and this is also the idea from the classical computation also. Now, when you think about quantum computation, there are many errors to handle instead of the classical computation. So the overhead is very large. So one way we are trying to achieve this fault-tolerant quantum computation is using this idea of surface codes. So this actually been recently implemented in the Google's device, like this paper here. And this is like the most prominent idea people think about implementing the fault-tolerant quantum computation. But one of the biggest overheads for this is number of physical qubits you need. So you need for almost 1,000 physical qubits for one logical qubit. So this is like a very large overhead we need to consider. So that's like one of the biggest drawbacks when people think about surface codes as like a prominent candidate for fault-tolerant quantum computation. Now, we can actually think about and also there's one more disadvantage being that like these are like these black dots are basically like a qubit. Now we need to individually address these qubits. So let's say we address these qubits, we should not address the other qubit like crosstalks. There's also another important error when we think about this surface codes, which we should avoid. But now we can think about another paradigm of quantum computation. It's also like a very standard paradigm is like the idea of harmonic oscillator. So let's say we have a harmonic oscillator, like we all have studied in like basic quantum mechanics. Is like a harmonic oscillator is like a system with infinite number of levels. Rather than just 2 levels, we have basically infinite number of levels. So, and one way people have been thinking and has been also been very successful is actually thinking about encoding a qubit in this harmonic oscillator. So we basically encode a 2-level system into this like infinite levels. And one of the most promising approach among this idea of GKP states, the Gottesman-Preskel-Kittel states. They're actually grid states. And also, this has also been experimentally demonstrated recently in the last year, where actually people have shown that we can achieve real-time error correction beyond the break-even using these like GKP kind of states. So these states have like the 0 and 1. The blue corresponds to the 0 state and 1 corresponds to the red state. This is actually the Wigner function, but without going into any detail. So this is actually an encoding we can encode in the harmonic oscillator and has been very successful and been considered as a very promising candidate for fault tolerant quantum computation. But here also there is actually a problem. So like we said, the basic qubit is encoded in a harmonic oscillator, but one of the problem is we need to entangle these harmonic oscillators. We need many copies if we need to do a very useful quantum computation, but entangling them could be tricky. That's another problem here. But today, now given these two backgrounds, we have the idea of qubits and also the harmonic oscillator. Now we are going to today try to like combine these ideas today. That's going to be the focus of today's work. So we can think about like an ensemble of qubits. So let's say we have qubits. So these are again the black dark dots are like the qubits here. So let's say we have a collection of qubits. And this is basically the system we are going to be interested today. And once we have these qubits, and what we can think of is like, let's say we have a collective interaction. So we don't need to think about interacting this qubit with this qubit or this qubit like individual addressings, but let's say we have like collective interactions between these qubits and like a symmetric interaction. So that's going to be the way we are thinking about here. So we have a collective interaction. And now then we are going to interact this qubit symmetrically. So let's say we like address this qubit somehow, and the addressing is actually symmetric for all the qubits. And now this actually, why this is important and interesting is that this is actually the paradigm people study in the case of quantum metrology. So quantum metrology is actually have a long history, is where people actually study these kind of techniques to estimate parameters. But now today we are going to take this into consideration to the case of encoding qubits actually. Okay, now what are we going to do? Like I said, it's actually very applicable for this like very promising setups like ion traps, BEC, and neutral atoms, where these kind of collective interactions can be employed like easily compared to the individual addressings. Okay, now given this collective interaction, like the setting, we can actually think about what we want to study. So the basic interaction lives in the symmetric subspace, and the symmetric subspace is actually characterized by a spin operator. We have this, let's say we have this n qubits. We can actually only think about symmetric operators, which is also like spin. So this is like these JIs, which are basically also known as angular momentum operators, are basically the sum of Pauli operators. So sigma J is like Pauli operators. You can define JX, JY, JC as just the sum of these. So you can define that. So what we have achieved here is that by just using this collective interaction, we can actually view this like a much bigger spin system. Instead of this qubits is like a big spin. So that's what basically we have achieved using this interaction. Now we can actually, and now given this, actually there is actually a one-to-one mapping between the harmonic oscillator and this ensemble of atoms or qubits. So let's say we have this harmonic oscillator, which has like infinite levels. This is actually like, let's say we have like a large number of qubits like collectively interacting. So this is actually a direct analog between these two systems. So the analog is known as the Haustin-Promakov transformation, and this is actually a well-known transformation and has been applied to like metrology. So in this limit, like this actually works in the very large n limit, but and need not be very large, but the large limit can actually define like we have the position, momentum, and number operators for harmonic oscillator, which is like the standard operators for the harmonic oscillator. They will become like the square root of 2n times jx will become the x, square root of 2n times jy will become the p, and then n, which is a number operator, will just be a n by 2 minus jc. So this is like known as the Haustin-Promakov transformation, and we can just use this here. So we can, whatever we have in the harmonic oscillator case, whatever codes we have, we can actually transform this to the case of this ensemble of atoms. Okay, now we can actually see like the GKP state, like I said, which has been very successful for the harmonic oscillator, can also be mapped to the spin system. So this is basically an example of a GKP state for this collection of atoms. So like this is like n equal to 100, and these are like the two states. So we have a 0 state and a 1 state, which looks like this. So we can take a take a closer look here. So this is basically the 0 and 1 state. Now, what is really helping here is that we have these states, and like we can see there's like a gap, like we can like these peaks, and there's actually well-defined gaps between the 0 and 1 state. There's actually a non-gap between the states, which can be extracted from the harmonic oscillator limit. And this gap helps in, let's say there's a small error which shifts this, like a small shift to this. You can actually detect this shift as long as this shift is small. That's basically the idea used in the GKP state. And we can also use that to advantage in here. So for this collection of atoms or like collection of qubits, we can basically use and we can use that such that we can correct for these errors in JX and JY. So that's going to be the idea to error correction. Okay. Now, given this code and this error correction property, we can actually take a look at the gates we need to implement. So that's one of the next things we need to do. So there is also, we can define these gates. So we need this C node. I'm already defining the Clifford gates here, the C node, Hadamard, and the phase, then we can create any Clifford gate using this. So we have the C node gate, which is basically the interaction of JX times JY. And then we have the Hadamard, which is basically the rotation by JC. And then we also have the phase gate, which is basically a JX square interaction. So these interactions are not very hard to implement and could be easy to implement for this like collection of qubits. Okay. Now, to further see the significance of these, we can actually take a look at what happens to these chords in presence of decoherence. Sorry. In presence of decoherence. So let's say we consider a simple model of decoherence, which is actually known as a stochastic relaxation. So this is actually the decoherence model given here. Now, we don't need to go into much details of the model. So if you need to know more, just ask me. But let's say we consider a decoherence model here. And now we can see the performance of this code. So this is like a fidelity as a function of this decoherence parameter gamma, which is lambda times t, as given here. And what happens is this is actually different kind of GKP codes, but we don't need to go into the details. But what you can see is that these GKP codes outperform all other codes in small decoherence regimes. And that is actually a very significant result. And you have these other codes like rail and binomial, which are actually kind of other codes you can create, you can consider for this ensemble of qubits approach. But here we can see that this GKP codes outperform all the other codes in here. And thus it seems like GKP code seems like a very promising approach. And with this, we can basically summarize what we have learned today. So we have seen that like a very new approach where you actually encode a qubit into an ensemble of qubits, and we only need collective interaction. That's like kind of the key point. We only need collective interaction. So this could be easier and maybe practically easy to implement in the current hardwares. Now, the next thing is that we studied one of the codes we could study in this case, like the GKP code, which has been one of the promising codes for the harmonic oscillator, and see that these outperform all other codes. And for more details, you can check the archive where the preprint is there. And Tyler Volkov is the partner in this paper. And if you have any questions, feel free to ask me or you can email me at here. And with this, I will just stop my presentation and thank you everyone for your attention.
Okay, very good. So does anybody have any questions now?
This is Terrell. I do not, excuse me, I do not have a question, but I want to compliment you on a very clear and understanding presentation, quite frankly. Much appreciated.
Yeah, thank you. Thanks.
Okay. So for every presenter, we normally collect some like brief bio information. Yes.
Adrian, excuse me, there is a question out there.
Where's the question?
I saw a hand up.
Where's the question?
Yeah, I have a question.
Yeah.
Perfect.
Yeah, I just wanted to clarify on slide 14, I think. Um,
Which slide? 15?
14.
Oh, okay.
Yeah, I wanted to confirm like the X and the P here, are they position on the momentum operators?
Yeah, that's true. So we have the
Oh.
position and momentum operator for the harmonic oscillator. So we can actually analogously define a position and momentum operator for the collection of atoms
Yeah.
or qubits actually. And then
Okay.
take all the codes from the continuous variable. So once we know that operators, so we define every code using that in the harmonic
Yeah,
oscillator. So we can basically transform that to here. That's what the basic idea is actually.
Okay, yeah. Good. Thank you. Just
Yeah,
so
no
it's
problem.
clear.
Yeah. Thanks for the question.
Very good. This is Tunde, correct?
Yeah, that's right.
All right, good. Anybody else? Any other question? So while people are thinking if they have questions, let me just say what I was going to say, that for every presenter, we collect a little bit of bio information, and then we ask them to describe the research in terms that a high school student would be able to relate to. And then we ask them about what their dream employers might be, just because when our industry partners would look at this, they probably can get an idea whether their companies are showing up or not in the list of preferences of the the quantum talent that we are trying to showcase here. So, and then there's also questions from presenters to the industry members. So, as far as dream employers for Siva, I think he mentioned Google quantum computing and AWS. He says that his goal in the future will be to focus on quantum error correction and to contribute to the greater goal of fault-tolerant quantum computation. One question for the industrial partners is what exactly are the key qualities that they look for in a candidate for a job? Is it okay if the background is different for the candidate than the specific, requirements for that position?
Well, if I could add something to that, I mean, different, in my opinion, difference is good. The last thing I want to do is hire somebody that is an echo chamber of what I think or do for one. It's hard to be different, but those who are different get paid better, quite simply.
Okay. So this is also an opportunity for us, I guess, to point out that the workforce development TAC used to and probably still has the goal of running surveys to find out the answer to exactly these questions. Am I sharing the right screen? I hope I'm sharing the schedule.
Yes.
And there's a chat that I never opened, I guess. So sorry about this. So I think I got a question from Ellen, but it's a direct message. Is that for everybody else? Ellen, should I read it out? I could. So I'm going to read it out. So Ellen, for some reason, she sent it straight to me. So just curious regarding collective qubit movement. I believe the Aussies used the crystal resonator to create a microwave cloud that covered the standard microchip, and the cloud moved all the qubits at once. The implication is the individual wiring to the individual qubits can be removed and heat reduced. I just don't know if it has gained traction. So she says, not sure if the question is relevant, but it's something interesting she wanted to mention. Anybody else? If nobody else has any questions, I just want to thank you very much for your presentation. We're looking at the schedule of presentations, and then we're going to move on to the next presenter, if that's okay. Thank you, Siva.
Yeah, thank you. Thanks a lot.
Our second presenter is a sophomore at Indiana University in Bloomington. His name is Edwin, and he is pursuing a degree in both physics and mathematics. He started working with his current lab group as a senior in high school. Let me stop sharing and let him share the screen. The title is Towards an Undergraduate Lab Apparatus to Demonstrate Quantum Entanglement of Gamma Rays. And this is Edwin and Shipp. Are you?
Thank you so much, Adrian. Hopefully everyone can see. So my name is Edwin Shipp. I've been working with this group for a while under Professor Mike Snow to create a lab to measure quantum entanglement for undergraduate students. So kind of a little bit of background why we decided to do this project. So it's a quantum sensing lab, and quantum sensing, quantum entanglement, quantum physics in general are kind of fields of growing importance. They have a lot of applications, of course, quantum computing, but also places like the medical field, PET scans, and things like that. Unfortunately, it's kind of a difficult subject to teach, a difficult subject to kind of wrap your head around. So we decided we wanted to create a tool for undergraduate classrooms so that students could get hands-on experience and learn about these kind of difficult subjects in a way that would better stick in their brain. We also received support from the Reichert Foundation, which is an organization that supports groups of undergraduates creating labs for undergraduate classrooms in physics. So that was kind of right up our alley, so we appreciate their support. So the physics, of course, trying to measure entanglement. So we get this entanglement from the annihilation of a positron and electron. This annihilation creates a gamma ray pair. And let me get my pointer here. In this diagram here, we can see is an example of this. We have our source in the center, emits gamma rays in opposite directions. The gray vectors represent their momenta. And then these orange vectors represent their initial polarizations. This also can be described this entangled state here, if that's more familiar, with the possibilities of a horizontal vertical or vertical horizontal. Of course, both of these are possibilities and we don't know which ones. We have to describe the system in this entangled state. So of course, to measure this polarization is our goal, but it can't be done in the easier methods like filters and things like that because of the high energy of the gamma rays that we're looking at. So we rely on the polarization dependence of Compton scattering. So this equation here is the Klein-Nishian and differential cross section that describes that kind of scattering angle. But you see there's two angles, not just one, that are involved in this equation. So there's theta and then there's phi. Phi is the angle that we really care about. It's the plane of polarization. That's what we use to measure the polarization of the gamma rays. This theta is the polar angle, and we selected a theta of 90 degrees because, as you can see on this diagram on the right here, that is the angle that allows us to have the highest resolution for this determining the polarization of our gamma rays. So the measurement we're trying to take, this is well, I'll start with this diagram. So we have our two polarization planes, and the angle between these planes is the angle between the polarizations of our two photons that we really care about. Now we can fit these different angles as a function of that phi value. Yeah, the coincident rate of these different angles, and from that fit we can pull this mu value that is our Bell type inequality that we can use to prove entanglement. Bell type inequality being a very famous type of issue, is the same kind of problem that was solved to win the 2022 Nobel Prize. It's not the same inequality, but a similar one to what we're doing. So our goal is to, of course, to measure mu to a high enough precision that we can say that mu is greater than 1/3, and then we've found in entanglement. This example on the bottom right is fake data we use to test our analysis, but it's what it might look like when we determine that we have found entanglement. So this is the apparatus that we've designed to take this measurement. The kind of core of it is this lead tower, which contains some sodium-22 that we use to create our positrons for annihilation. And then on either side of that tower, we have an assembly that looks like this. So in this image, it only contains half of the full apparatus. So the gamma rays come out of this lead tower and they interact with this active scatter. That's where the Compton scattering occurs. But instead of just a chunk of aluminum or some other material, we chose to actually use a scintillating plastic with a photomultiplier tube connected to it. So when the Compton scattering occurs, we can actually detect that event, which just helps with our data analysis and our event selection to get rid of any noise. And then from that, it goes into one of these 4 detector boxes. Each of these boxes contains a barium fluoride detector that I'll talk about more in a minute. They're light tight and they're at various azimuthal angles, as you can see. Each of these detectors is also mounted on a rail, an 80-20 rail that can be moved closer or farther away from that active scatter. And there are a lot of elements like this that allow the students in the lab to kind of cater their measurement to exactly what they want to do. So it's not the same for every person. They can get a better kind of interactive grasp on the material that they're working with. So on top of being able to move closer and further away, all of these detectors also spin on an axis around the active scatter. This has many reasons that we want to do it that way. For one, it helps us average out some of our uncertainties within the detectors. If two detectors have slightly different characteristics, we can switch their positions, and then those uncertainties will average out. It also allows us to get a better fit for our inequality here. The more discrete angles for phi we have, the better of a better fit we can do, and the more certain we can be about our Bell inequality. All of this assembly is also stacked on top of some 80-20 supports that allow the entire this chunk of the assembly to move closer or further away from the lead tower, which is again just another degree of control that the students have over the experiment. From the back side, you can see this is the way we chose to kind of manage the angle selection for the rotation of the detectors. There's just a flange on the back with a pin that can be set different discrete angles. And we have another piece of 80-20 attached to the active scatter that allows us to pull it in and out of the apparatus without having to disassemble the entire thing. So our detector boxes are light type boxes that we've created that have magnetic shielding, and then our detectors. So the detectors we got from another project that happened about 10 years ago at IU. They sent about 1,000 of these barium fluoride detectors up in a balloon in the Arctic to measure cosmic rays. And so there's a few characteristics of these detectors that we're able to take advantage of. One is they have their own built-in voltage multiplier. So we only have to provide a voltage of 1 or 2 volts, which is nice considering we have many detectors instead of having to apply thousands of volts multiple times. And they also have these barium fluoride crystals, which are the scintillating crystals that have some special characteristics, and we like them for a few reasons. One is their insanely fast rise time, so we can get a very good time resolution. They have a rise time on the order of 800 picoseconds, which allows us to, even within coincidence events between two detectors, we can find the timing between when two gamma rays hit the detectors and allow us to do even more event selection with that. Unfortunately, these crystals, instead of emitting light in the visible range, which is what our photo multiplier tube is able to view, they emit light in the UV spectrum. So we also have to have this wavelength shifter, which we use TPB for, that shifts it back into the visible spectrum. There's some lead shielding to prevent other scatterings from other places, gamma rays coming in from where we don't want them, and more collimation on the front. The metallic shielding to avoid any discrepancies caused by magnetic changes in the magnetic field is because these detectors are going to be rotating around, changing orientation within the Earth's magnetic field, and we didn't want that to be a factor of our measurement. Also in the top right is an image of our active scatter. It's smaller, it doesn't have as good energy resolution or timing resolution. It's just used for that event selection. So after our detectors, our signal pathway goes through some NIM and KMAC electronics. Our current setup is shown here on the right side, and then kind of the final plan in a block diagram is shown in the bottom right. I won't go through the whole thing, but the most important parts, we have our quadruple coincidence unit, which basically allows us to do coincidences between the two barium fluoride detectors and the two active scatterers. So we can say with high certainty that the events that we're looking at are the events where a gamma ray has been scattered at both sides at the same time. And then after more processing, it goes to an ADC, analog digital converter, which allows us to store that data and view it on a computer. The rest of our post-acquisition analysis we use mostly during Python, but we're trying to develop the analysis in parallel in Python and in Root so that students have the options between which language they prefer, which language they'd like to learn. Down in the bottom left here is an example of a spectrum that we've taken. This is just with two barium fluorides. This is before we've integrated the active scatterers. So the x-axis here is the energy levels in one detector, and the y-axis is the levels energy level in the opposite detector. And as you can see, our peak is right here at 511 kiloelectron volts, which is the energy level of the gamma rays that we're looking at. So this is where we expect all our data to be. Each point here being an event where both detectors received a signal at the same time. But there are also these shadows to blow into the side of this. We're not surprised to see these. This is probably caused by some sort of scattering off of something else in the room, or the lead collimation happened to go into one of the detectors at the same time as a 511 gamma ray did. And so within our analysis, we can get rid of and ignore these events. this graph here, the array of graphs, shows what our analysis will look like when we have all 8 detectors in place, having 16 pairs of detectors between those. This is fake data that we've used to test our analysis. It's actually just this spectrum repeated 16 times. But when we do have all of our detectors set up, we'll be able to take all of these spectra, do these fits to each one, and then pull the parameters out of that so we can do our Bell inequality fit, and hopefully measure a value of nu greater than 1/3. When that's all complete, we'll be able to disseminate that down to students in classrooms so that they can perform the measurement for themselves and get a better understanding of quantum entanglement, quantum physics. So it's kind of an update to where we are right now. We've ordered parts for the apparatus, we'll probably begin construction of that within the next month or so. We've also started doing quadruple coincidences, integrating both the barium fluoride detectors and the active scatters, and that's been successful so far.
Okay, wonderful, Edwin. So while people are thinking if and what questions they have for Edwin, let me just mention here in category dream employers, he said, I plan to attend grad school. He's a sophomore, as I said. After receiving my bachelor's, he has not thought much about where yet or what he would like to do afterwards. But in some sense, you know, in terms of internships, for example, this would be relevant in with respect to connecting to some of the industry members. So don't forget that is maybe if Terrell has that information, you can post a link to where people can register for the Thursday session, because office hours with industry mentors are resuming Thursday, as far as I can tell.
Yes, true.
So any questions for Edwin?
Yeah, Adrian, I have a question for Edwin.
Very good, Sean.
Yeah, so I guess what would be your biggest learning experience over the course of this project? Doesn't have to be academic, but I just like what's your largest takeaway from what you've done and contributed to this project so far?
Yeah, thank you. So I've had to learn a lot through the course of this project. I've just finished my freshman year, so I pretty much all of the physics that I've learned involving this project I learned while taking measurements and doing things like that. I had to learn a lot about just the process of being in a lab. That's a new experience to me. And I think it gave me a kind of a good idea of what it'll be like for the students performing this lab when it's an actual lab in a classroom. So I think I kind of bring a unique perspective to that. But it's been it's been a very valuable experience. I've learned both in academics and just in kind of work style and what it's like to be in this kind of environment. So it's been, yeah.
I think there's a question in the chat from Ellen. Who else has a question?
Terrell has one when we finish Helen's.
So Ellen says you go from gamma non visual light to visual light to the use of a filter with some regret, seemingly. Please advise. That's what she says in the chat.
Yes, so I can go back. So the gamma rays coming out of from the result of the positron electron annihilation are very high energy. So the way we look at those is with the barium fluoride crystal. It interacts with the crystal in that way, but it only produces UV light, which is still higher energy than we can look at with our photomultiplier tubes. So then the TPB is the wavelength shifter that shifts it up just another notch to where we can look at it, but we maintain energy resolution. So we can still tell the difference between high and low energy gamma rays, but we only look at them when they're at lower energy afterwards.
Edwin, I just have a quick question. If I didn't have anything lying in the lab, do you have any handle of how much this equipment costs?
Yeah, so that's a good, so a lot of them, luckily, we didn't have to pay for in-air detectors. That would be a very expensive thing. But in terms of in terms of the things that we've had to purchase for constructing the lab apparatus and things like that, it's on the range of a few $1,000s. Yeah, which is much cheaper than many other options for quantum entanglement labs and things like that, which is a big goal of ours.
Yeah. Thank you.
So this would be good to have an industry member here say, we do this and we do it much more expensively than you, or we actually have a kit that is available at, so at the plenary, there were some people who came and talked about the hardware that they had and then customization options, but this is a good question. Terrell, I think.
Hi, Edwin. Yeah, thank you for the presentation. Quick one. I just wanted to confirm, like, is this some standalone lab or is it like in conjunction with some course that students have to take? How do you plan that?
Yeah, so specifically in university, at least there's a senior lab class that students have to take. So this would be one of many labs that students would participate in over the course of a course. Yeah.
So the benefit of this, as Sean was pointing out and Edwin, I think, confirmed, is that I worked on this. I understand it now. I can build stuff. I can teach other people. I just want to remind, so we don't forget, that Katarina mentioned last week that it would be really good if the industry, I don't know who actually brought it up first, the gentleman from University of Delaware. It would be good if the industry would actually donate the equipment that they no longer use, currently, and then basically they could be used for parts, or they could be used to beat them in terms of or match their performance, and that would be very convenient for such a project like this, to take parts or the systems from industry and just incorporate them. It would simplify the prototype in some sense, maybe, hopefully.
Absolutely.
So did Terrell still have a question or not?
Yeah. Edwin, if you don't mind, I'll get a little less technical here. Places, as an undergrad, I'm a little beyond undergrad at this point, but there's a lot of programs at IU. Let's just look at IU, for example. There's a lot of other programs out there that are a heck of a lot easier to get through, and so on. Business is probably 40 year undergrads are probably in business school. What for you, what takes you to this field?
That's a great question. So what takes me to India University is that I grew up here. But in terms of what takes me to physics and that kind of thing, it's a great question that I'm still kind of figuring out, but I've enjoyed the journey so far. I think I will continue to do so. But I always liked math through middle school and through high school and things like that. I took physics in high school and loved that. And like I said, or like Adrian said, in high school, I started working in this lab, and I got a kind of an itch for lab work and experimentation that has carried me through that. So it's just something I kind of am continuing to fall in love with.
Well,
So
I guess you don't have to have a tangible reason, but keep up the momentum.
Yeah.
I was kind of like that when I was younger, but I lost the momentum. There was a lot of rock and roll going on in the 70s and 80s. It distracted me, but good.
There's a subjective and an objective component to Edwin's answer. I mean, so the first thing would be, he seems to be interested in this topic. And I was going to ask him, but I'm kind of running out of time. However, the idea was, he started this in high school. And I was going to ask, south or north, but it doesn't matter. Were you, Edwin, a unique person? Was there anybody else involved in quantum, or you were just the only person?
So my process, at my high school, there's an internship program that you can do, but it's very kind of self-driven. So my process to get in this lab was emailing as many professors as I could until one of them responded. But it just by happenstance, there is another student who we've worked with. I think he's accredited at the beginning too. Liam Boltman is also a high school student when he was working in the lab, completely by happenstance. But I think the two of us are the only people who had internship placements in academia at all within my high school. So it was definitely not the most common thing.
I see, from high school north, and they have a very strong science Olympiad team. And the
That's
other
true,
component, the other component that's very subjective, Terrell, is that once he has the interest and comes to IU and he sees the quality of the people around, he says, well, I guess I would love to work here because it's so exciting and these people are so passionate as well. So it's always a subjective and objective component.
Exactly.
Okay, I guess, thank you, Edwin, for this. And we're going to move on, if that's okay, to the third presenter. So from Southern Methodist University, we have Tunde Kushimo. He is a physics educational researcher. He has a master's degree in physics from Texas Tech University, where he began his research in quantum computing education. I'm not sharing the screen. He's going to start sharing the screen. And the title of his presentation is Investigating Students' Strengths and Difficulties in Quantum Computing. Let me start by mentioning Tunde's question for the industry members. He says, do you think, he says, could you please help with a list of internship opportunities for a quantum computing education researcher like me? So the idea is, where would they fit in industry? That's the overarching question. But Tunde is going to start presenting his dissertation.
Yeah, thank you so much, Mary, for this time. I'll actually be talking about something different from what everybody has been saying so far. Like I know many people have been talking about technical part of like quantum computing. How do we achieve entanglement? How do we investigate this? How do we do correction? That. My own research actually deals more with how do we teach this and how do we learn it, right? It has more to do with how do we produce most of like the researchers and the scientists that have to like take up the challenge that we have right now. And so I started this research while at Texas Tech University doing my master's degree. I've always been in physics, right? I had my first degree in physics from Nigeria, and I've been a physics educator myself for like over 5 years now. And I've kind of like interacted with students, and I kind of understand to a large extent how teaching and learning happens in the classroom. So my reason for coming to the United States actually was more of doing some physics education research, but I stumbled upon quantum computing, and here I have like doing some quantum computing education research, because I believe there's a very like strong link between the two. So I'm going to be talking about, I'll skip the first part, which is more like introduction to quantum computing, because I believe everybody actually has like a basic background when it comes to like quantum computing. So I'll move quickly to the research itself, like what I've been doing regarding quantum computing education research. It was actually the wave of universities teaching quantum computing, to undergrad and even introducing it to high school students. And my professor back then at Texas Tech needed to teach the course like in the physics department for the first time. And so we had to like sit together to see how do we design this curriculum? Like what exactly do we need to teach and how do we go about teaching? But because that was the first time teaching the course, like we went through quite a number of important topics that we think we need to cover, like for an introductory quantum computing course, as it were. And so, like after that, we went on to say that, you know what, we think that there are actually like ways to go about improving the teaching and learning of this course, at least to a first timer, at least to somebody that probably does not have a background in physics or background in chemistry or background in math or computer science, as it were. And so we hypothesized that, see, students definitely will gain some strength learning about quantum computing for the first time, because maybe there are things they'll be comfortable with at the first, exposure to the whole field. And we also like thought of it that, of course, students would also have some difficulties that they would be dealing with, as teaching and learning happens. And this was what informed this particular research. And this has actually been like the motivation behind my research, like even so far up until now. So for this particular research, we're actually like investigating the strengths and difficulties of students, particularly senior and junior students, when they take quantum computing course for the first time. And for that investigation, we used the student that took the course for the first time. We designed some sort of like interview, like more like open-ended interview questions, just to check with the student and see what are the strengths and difficulties they actually had out of class, and how do we help them like get better at learning. Because now this is more like an overview of the class was quite small. We had 5 students, and good for us. All of the 5 students volunteered to be interviewed, and this is more like they're all physics majors, and just one of them had experience with classical logic gates because he actually took like some computer science courses that taught him that. But one thing that was common to all of our students is the fact that they've been introduced to quantum mechanics at some point during their studies because they are all physics majors. Right. So that's about, so the teaching method that we actually used at that time for the course was more of a flipped classroom style that was more student-centered approach, student-driven. We have them because one strong tool that we used during the course was IBM QED and the IBM lab, like virtual lab, where students had to like go online to code. And this is stuff that we do in class because I was like the teaching assistant, of course. So this is stuff we do in class. We have students go like do some study, and then we come to class to see, okay, where have you stopped? How do we do about overcoming this obstacle at this time? So yeah, and for the data collection, it was more of an open-ended questioning and answering session. We had 2 sessions of interview for each student that volunteered. And what we did was to have some interview questions set across all of the topics that we taught in the course. And let me quickly mention that the interview was actually conducted a semester after the course was taken. We actually did not conduct this interview the same semester as when the course was taught, because we wanted to know what exactly the student has what exactly they internalized, what exactly did they take out of the class, not something that they can easily flip back at their notes on and just answer the questions. We wanted to see what they took out of the class when they had it. Now this is more like a sample question of what we gave the student during the interview. Like you see down here, we actually have, down here we have some probing questions, more like some follow-up questions, just to check our student understanding and also to see what is their difficulty. You know, we get to understand that, oh, a student understand this question or a student understand this concept or this topic based on how they respond to question. What is the wait time? How confident are they when they answer these questions? And you know, students sometimes outrightly will just tell you, you know what, I think I don't know this. I think I've forgotten this, even though I know we discussed it in class, but I don't fully understand. And I'll show us a couple of examples of student statements, even from some of our recordings. This is a typical interview session. We provided them with some writing materials just to, it's more of a think aloud process. You know, this is students working through some quantum circuits, just explaining through based on their understanding and the question that we have. Yeah, this is some think aloud session. Now, for the data analysis part, we actually, like I said, we recorded every session, and then we had to go over each recording to see patterns, to see some striking common facts to each of the students, just to be able to say, oh, this is substance that is common to all of our students, and this is something they all are struggling. This is something they all have difficulties. And so, yeah, after doing all of that, we have the result that we have from analyzing our data. We actually found out that students understood the concept of measurement. Now, I know measurement is a big thing when it comes to quantum physics and quantum mechanics itself, but when I say students understood measurement here, I mean students understand that things are probabilistic, this is not definite, right? And they understand how the amplitudes play important role even in taking measurement, right? And we also noticed that students were more comfortable and with matrix operations. Give them any questions. I can say, from our recordings, from the data that we have, almost all the students want to solve questions using matrix. They hardly go to the direct method of doing this. Now, this was something we found common to them, or maybe because I was still trying to brainstorm on the reason for that, because we think, okay, maybe because they are physics majors, maybe because they've done some quantum, or maybe because they have linear algebra background, right? But still trying to see. But something important to us is that as much as students feel comfortable with metrics, they also need to find a way to balance all of the methods that are necessary and important when learning about quantum computing itself. Because you agree with me that matrix operation, as useful as it may be, it might be very difficult to apply that to some algorithm, to some like trying to do some calculations using metric operation would actually be a tedious one compared to using Dirac and understand some symmetric and how to do some eliminations, as quick as possible. We also found that the students were comfortable using, they quite understood blood sphere and how information can be represented in that. And also, they had good understanding of how the poly-hex and the poly-Z gates operate, including the Hardeman and especially the controlled X gate, but not the other ones like the rotation operations were quite difficult for them. And exactly, even the phase kickback was a major one. Now, this particular question I shared here was actually a question on the phase kickback. We noticed that students understood how the C0 gate operates when the controlled qubit is in either the 1 state or the 0 state, but they had difficulty seeing how things happen when the controlled qubit is in a state of superposition. And that was something we actually like noticed, that these are some of the pictures showing how students answered some of the questions. And like I said, these are some of their statements, from the recording. These are some of the transcripts we got. There was a question that says, oh, can you talk me through the quantum circuit and when each gate, what each gate does? And good understanding of the C0 gate, says that, and that's a picture of a student just doing a step-by-step approach on navigating through the whole quantum circuit itself. Now it says that when this C0 acts upon the state, because the controlled qubit is given in state 1, the target qubit will then be a value of 1 from 0, right? Now that's a good one. But the challenge there that we noticed was that they had understanding of that. These are some of the strengths also, like I said, because of our time, I won't go over that. That was why I did a quick summary of the table over there. This is a student actually going through step-by-step explanation of what happens across the quantum circuit. Yeah, quick one. Yeah, like concerning the example I give about phase kickback, this is some, I'm just gonna bring out a particular statement that one of the students mentioned. Sorry. Now, right here, I guess the C0, now the question was, what do you understand as phase kickback? And phase kickback is actually it's very applicable in most of the quantum algorithms that we see today. When you talk about ancillary QED, you're trying to work around controlling some qubit, then you actually need good understanding of phase kickback. Now, the student responded, I guess the C0 does nothing on the qubit since the control is in a superposition state and not state 1. So that's suggested to us that there's a challenge understanding how control gates generally would operate when the control qubit is actually in a superposition state. And that's something we actually want to help our students overcome, such difficulty. And for a follow-up, actually, we are working on some evidence-based material on how to help students improve the learning of quantum computing. I know this might sound like this particular initiative that we are bringing is what we call multiple representation learning and assessment material. And the idea is actually to walk students through their difficulties using their strength, right? I know this might sound like counterintuitive to some physicists because we believe that having multiple ways of representing an idea is actually one of the major problems in quantum physics generally, because you have all of the different representations flying around, and then you have a challenge knowing which one exactly to use at what time. Now, this is just a quick sample of what we are working on. Like I said, it's a multiple representation learning and assessment material where we have students solve the same question using different methods. It's the same thing. And the goal is this. The goal is to help them reinforce their strengths and at the same time help them overcome their difficulties. And we say use what they know to overcome what they need to know, right? So that's the whole idea, that's the whole concept. And for this particular sample question, this is how to walk through the solution. This is the matrix doing the same thing, Dirac doing the same thing, the Blossfeld doing the same thing, and then we have them. Now, this particular ending part is, for me, is the most important because this is where the students get to internalize what they've learned. And we say, walk me through the step-by-step process of this circuit. In your own words, can you explain what is going on? And this is where we get to know if the students are already internalized the learning or not. And yeah, so right now that's what we're working on. And we have a publication presently under review concerning that, but you can always have like a preprint of work online at this link. I want to thank everybody for your attention and thank you for the advice.
And I thank you very much as well. And as people think what questions they're going to ask you, I just want to say Tunde says that his goal is to become a quantum computing learning and development specialist, designing, developing, and delivering training programs for quantum computing workforce. It is his dream to intern or work at some of the firms such as, let's say, IBM Quantum, Microsoft Quantum, and Google Quantum. And the reason is they already have established programs for quantum computing education and workforce development. So anybody, any questions? Thank you, Tunde.
Thank you.
Adrian, I got a few comments if you don't mind.
Oh, go ahead, but you want to make them too?
Very quickly. Yes, Tunde. The presentation was fantastic. I think quantum education research is something that needs to be paid more attention to. I'm also working in quantum education research right now. And I just wanted to say that I know that I thank you and appreciate you for doing the work that you're doing right now because other people out there, please reach out to me. I think your presentation was great. Awesome.
Thank you.
Let me add, yeah, thanks for the presentation. It's really good to see that, some folks are still interested in social sciences and, what you're doing by going through this research, this qualitative research is really, really important in a world now that we're just facts are opinions. And I was impressed that your study, for one, teased out what I think is a huge problem in learning in general, but in particular in STEM fields and obviously in quantum, and that is, what's the word I'm looking for? The different notations and the different languages used by different disciplines to describe the same thing. For example, in machine learning, we got principal component or SVDs, but in statistics, we call it principal component analysis, and they're essentially identical, but completely different conversations.
That's right.
And so, in my experience, because I'm a late learner in quantum and physics and all that, I come from B school and social sciences. That was the biggest challenge I had. You read one book, it's telling you A, but using language X, and another book telling you about A, using language Y. And only until I truly understood the topic could I realize they were talking about the same thing. And I think that's a huge frustration for everybody.
Yeah, I would actually like to make a comment on that because that was one of the things we actually observed with some of our students now, because you have different authors out there, different textbooks. It was actually difficult for some of our students to read and study outside of the classroom because of this notation problem. Right. And one of the difficulties we actually like wrote down there is the fact that we need to find a way to agree on notations for quantum computing, because this again is going to help with the teaching and learning generally.
Well, I would make the point that, maybe homogenizing it is not the right answer. Because not to go off on a tangent here, but the goal is to understand something, no matter what notation you use, Dirac notation or something else. And if you homogenize it, it may actually reduce the opportunity to truly understand it. So I'm not saying it's necessarily a negative.
Yeah.
You know what I'm trying to get to?
Yeah, I get what you're saying. I get what you're saying, and that's what we're introducing in the learning material we're developing, like having different methods, but saying the same thing. Now, when I mean agreeing on some things, like generally in quantum computing, is actually like it has to do with some of the gate representations, representing qubits, sometimes from the left to the right to the left. That's what's a confusion for students. You want to represent a state of say 1011. Now you need to know if you are making like the qubit, if you're arranging a qubit from the left to the right or from the right to the left, because that is going to inform how you need to write that. Because if you're using different representations, then you have different state and that was what I meant by finding a way to agree. But I completely agree with you on teaching. It's a diverse world, and we cannot like constrain people to learn. And what I've learned about students have different strengths. Some students are visual learners, like they just want to look at the images and boom, they have it, saved somewhere in their brain. Some students need to go through like the step-by-step process to be able to internalize things. So we need to like put all of those out there and learn students, just because one of the things that we do is going to help people even feel more comfortable learning quantum computing.
And I'd make the point, just to end this question or comment, if I may point out Edwin, right? So Edwin, he's a motivated dude. And so if he has to learn 6 notations, he learns 6 notations.
That's right.
That's our challenge at the core with quantum, and in a broader sense, globally now, just STEM education, because, it's work for many people. It's work. Edwin, I think it's more like play, but anyway, keep up the good work. Appreciate it.
Thank you.
Okay, so I'm going to change the screen. I'm going to share my screen. The one comment that I want to make, first of all, thank you, Tunde. Look, today's May 23rd, and there's this presentation here that Tunde just made. I'm trying to highlight. And this is a physical education research presentation. And then we had, Tunde may know these people because they work in the same area. This is another presentation from a physical education researcher. And that's one of 4. And then before that, again, we had from Oxford University, Caroline ten Halter. And the goal that we had since last year, when Josephine came and talked, was for every session that we run to have one physical education research presentation. On account that, it's good to have these presentations where people bring up concepts, they push forward the field, but at the same time, since this is the workforce tack, people need to either upskill or learn. And even teachers need to be trained so that they can then do a better job in the classroom. For example, in this case, unless they have super motivated students like Edwin. And I believe that this is a relevant topic and a meaningful topic that we need to keep including in our sessions. Otherwise, I wanted to say that if you have more than one representation, when you can calculate something in more than one way and get the same result, then you are a little bit more certain that what you're doing is in fact correct. And so the difficulty of the many representations is to figure out which one should be first. And then I want to mention Terry Rudolph's system that could come first. I want to mention the ZX calculus and quantum in pictures from the people at Oxford, Bob Kuke and Alex Kissinger. And then based on those, all the techniques that one uses to introduce these topics until you end up talking the language of the experts. I think Terrell says that there was a question in the chat. Ellen says, are the slides available? And I believe that the slides are not available because somebody has to collect them and there isn't anybody to do that. But we do record all these sessions. And so any of these presentations can be watched again on the website. I think the vast majority of them are recorded in 2020. Some were not recorded, but then since all of them are recorded. We're in a transition year. We're moving things from one side to the other and trying to institutionalize this program. Any other questions for Tunde before we move on to the last presentation? So I guess no other questions. I want to thank Tunde for the presentation as well. And now James Cummins is our last presenter. He was born and raised in Chattanooga, where we had our last plenary. He's a PhD student in the Applied Mathematics and Computational Science program at the University of Tennessee in Chattanooga. He received his Master of Science in Applied Mathematics from UTC in spring of 2022. He plans to graduate in December of 2024. Upon graduation, he hopes to stay in academia to continue research and advise future graduate students. So I think you're sharing the screen. Go right ahead, James.
Yes, can everyone see my screen?
I can.
Yes, okay, cool. All right, thank you everyone for having me. Again, my name's James Cummins, and the title of my presentation I'll be giving today is Hard Arrhythmias and Their Connection to Quantum Mechanics. So the project that I work on revolves centrally around the idea of hard arrhythmias. So they are basically a irregular wavefront that travels throughout the heart, and that causes the heart to contract in a irregular way. And we see this irregular pattern form in their heart. So a regular heartbeat would be like a radial wave that would circulate outwards. And in some arrhythmias, such as atrial fibrillation, the irregular wavefronts manifest themselves as spiral-shaped wavefronts. So cardiologists call them cardiac rotors. And these cardiac rotors have been investigated for a while, and the ways that we treat them have been somewhat unsuccessful. So that's where our project steps in, and we build a mathematical model of how these rotors travel in the heart. So in the process of trying to eliminate the cardiac rotors, first a cardiologist would map where they think the rotors are. This is a process of surgery where they put the patient to sleep, they insert electrodes into your heart, and they induce rhythm into your heart to try to locate where these rotors are traveling. So once they locate the rotors, they perform a ablation procedure. I've traveled with my colleagues to witness these ablation procedures and how they work. And they essentially burn areas into your heart to disrupt the irregular wavefronts from forming. And the idea is it acts almost like a roadblock of sorts to disrupt the spiral wavefront, to break it up, and to resume a normal type of rhythm. So the location of finding these rotors, the way they do this, because in my mind, they're doing this blindly, you can never really see these rotors, is they use the Doppler effect. And it seems like we have a lot of people from physics here, so we don't have to go into detail about what the Doppler effect is, but essentially a increased frequency, we would assume, means the source is approaching us, and a decreased frequency means that it's traveling away. And what our goal is, I'm sorry, let me see. Sorry, this not working with me, one sec. So our goal is to model the path of these cardiac rotors that's traveling between two equidistant electrodes in the heart. So we assume that the spiral is traveling between them, and we measure the frequency of the electrode that interacts with the spiral. Sorry, it looks like I'm having some trouble with my computer, one sec. sorry. Okay, one sec. So here is our, sorry, my computer is freezing. Here we go. I'll just start right here.
No problem. Just take your time. Do the best you can.
Yes. Sorry about that. It looked like it just wasn't one to click over to the next slide. So here is our rotor. This is a depiction of a rotor that we would see here. And our first idea that we take for a general candidate for the shape of this rotor is an Archimedean spiral plotted in polar coordinates. And we assume that the rotor is traveling towards the electrodes with a constant linear velocity and a constant angular velocity rotating in the clockwise direction. And we should see electrodes here. One sec. I'm sorry. I don't know why this is glitching up. Excuse me. So we should see electrodes here, and they're placed the same distance in the y direction from the center of the spiral. And in Doppler effect, we would assume that both of these electrodes would receive the same type of frequency. Now we see that with a spiral, if my slide will work correctly, hopefully this will move on, that with a spiral, we would see something that is not typical of a Doppler effect. We would see something like this, where the rotor is traveling towards those electrodes. It's just now past it. And we would see one electrode being intersected by this wavefront, but the bottom electrode is not being intersected. So this really messes with the cardiologist's ability to locate these rotors, because in one perspective, they may think it's increasing, meaning it's coming towards that electrode, but then from the other perspective, they may think it's traveling away. But when in fact, in this picture shows that the rotor is right on top of the electrodes they have placed in the heart. All right, one sec. So sorry, I don't know why it's being difficult with me. So once we have a model for our cardiac rotor, we assume trying to find different candidates for the spiral-shaped electrical wavefront. So through various readings through the research, we were able to see that the linear diffusion equation actually produces a spiral-shaped electrical wavefront. So we use that in the, sorry, I don't know why this is doing this. We use that and we assume a separation of variables in this form in equation number 3 in solving the diffusion equation. And we assume further that because of the relation of the size of the spiral and in the atrium that the spiral is traveling in, that we can assume that geometry doesn't have any curvature in relation to the size of the spiral and the size that's and the space that's traveling in. So we can assume for it to be flat. And once we do that, we're able to derive an equation in terms of our radius of the spiral to actually plot it. So hopefully this will come up soon. Okay, one sec. Okay, so here's our equation here. And this involves the Bessel function. This is this expression here. And this is with an index of 1/2. And we were able to reduce that further. I saw some people saying that you test your numerical experiments all these different ways. So we were able just to re-verify just through a lot of complex arithmetic that we had the right type of candidate for the spiral. We plotted this in multiple of different ways. All right, let me see if this will move on. So here we see with the spiral of m equals 1/2, we see a spiral that's very similar to the depiction seen by the Archimedean spiral. So this is a good candidate for our cardiac rotor. For values of m equal 1, we have a 2-arm spiral. For m equals 3/2, we see a 3-arm spiral. And for m equals 2 or 4/2, we see a 4-arm spiral, right? So it became pretty apparent that through these numerical experiments that this is the spiral we should be concerned about. And we applied that to our model and watched it interact with electrodes. And we were concerned about what were the differences between the Archimedean spiral and this diffusion equation spiral that we produced. And the key characteristic of the Archimedean spiral is that it should have the same distance between the wavefronts no matter where you're at. And if you look at this diffusion equation spiral, we plotted these red dots here just to show that we were measuring the distance between here. And the distance between these 2 points is the same between all the other 2 points, with the exception of the distance at the origin. And you can almost see it with your naked eye, that they're all uniform with the exception of that 1 point. And it turns out that will have some effect and as to how that interacts with the electrodes as the spiral travels towards it. Okay, let me try to get this to work again. Okay, so in comes the quantum story of, so we've modeled first this interaction with a Archimedean spiral, then we do this with a spiral from the diffusion equation, and we were wanting to test the nonlinearities and how that affects our spiral. So if you look at the diffusion equation, you could almost call a parent of that would be the nonlinear Schrodinger equation, because it has its nonlinear terms here. And these nonlinear terms will affect actually the shape of the spiral. And even more generally, we have a equation called the complex Ginzburg-Landau equation, which is kind of like a godfather equation of the nonlinear Schrodinger. So for a special case in the complex Ginzburg-Landau, we're able to get the nonlinear Schrodinger. And for special cases of nonlinear Schrodinger, we could kind of get this diffusion equation. So we wanted to test our nonlinearities and see how that affects the shape of the spiral. So here today, we're just going to talk about the complex Ginzburg-Landau equation. And we assume that our equation is going to be in the same form that it is that we had in the linear diffusion equation, sorry. And we go about trying to solve the complex Ginzburg-Landau equation. And here is a plot of one of the spirals that we see for the complex Ginzburg-Landau equation, and that's at t equals 8 seconds. So this has Neumann no flux boundary conditions. So as this interacts with the boundary, it's going to like reverb outwards. It's not going to be traveling past it or anything like that. But we're not necessarily concerned about trying to do anything like that, because we essentially want like a plane wave, like snapshot solution of our spiral, and then have it travel towards these electrodes. So here's like this spiral produced in like the quantum sense. And here would just be a better depiction of that spiral instead of a contour plot. You can kind of see here's R and theta, and for the z-axis, that is a plot of just the real part of our solution. And you can even see in this picture here that you can see those peculiarities at the origin, right? For the Archimedean spiral, it would curve perfectly towards the origin, and we don't see that in this type of picture. Let me see if I can skip over to the next picture. And here's another angle of looking at that. You can kind of see how beautiful that is. One really fascinating thing about this is the research that I'm particularly involved is in atrial fibrillation, where we have these two-dimensional flat spirals. But in ventricular fibrillation, which is a very serious episode, someone could live their whole life with atrial fibrillation if it's a mild case and not even know it. Someone with ventricular fibrillation would need to go to the hospital immediately. Now, it turns out that these three-dimensional spirals, cardiologists actually call scroll waves, and these scroll waves are a large culprit of ventricular fibrillation. So they're all related to one another. Now, as you know, I know we have a lot of physics experts here. This is what you would expect to see for the Doppler effect, right? If we have electrodes, let's say that they're positioned, and as long as the electrodes are at the same angle of the source the whole time, meaning that they're the same distance away from that center, then they're going to perceive the same frequencies. And as it's coming towards you, you'll have an increase. And as it moves away, you'll see a decreased frequency, right? And right as when the source is perfect with you, you will both perceive the same frequencies. Now, here's what happens with the spiral. First, we just show a linear rotating wave. So just a rotating wavefront. We'll see the strikes to the top electrode in red and the strikes to the bottom electrode in yellow. This dashed line shows where these electrodes are positioned. So you'll see here that in one respect, you'll see an increased frequency for one electrode, but a decreased frequency for the other. Now, for the Archimedean spiral, we see some oscillations here as it approaches, but the same general type of behavior. For the top electrode, we see that in blue, and the bottom electrode in green, increase coming towards or decrease coming towards, depending which electrode you are. All right, and there's a lot of other things we could go into detail here, but these are the main key observations here. Now, here is what it looks like for the diffusion equation compared to the Archimedean spiral. So same general shape here. For red, we see the top electrode strikes, and in yellow, the bottom electrode strikes for the Archimedean spiral. And in blue, we see the top electrode strikes for the diffusion equation, and the bottom electrode strikes in the green plots here, okay, for the diffusion equation. And same type of general pattern. We see these oscillations like we see with the spirals in general, But here for the top electrodes, and also probably here for the model electrodes, this is where we see these peculiarities towards the center most likely. And this is how that's affecting our frequency, because as the rotor approaches the center of these electrodes, that's the only part of the spiral that's going to actually interact with those electrodes. So these are our results that we see with that. And hopefully this will aid cardiologists in trying to locate these rotors, which would provide a better ablation procedure. Now, the stuff moving forward that I plan on working on is I specialize a lot in numerical analysis, and I do a lot in machine learning. Kind of one of the emerging fields right now is physics-informed neural nets. I'm sure you all have heard about it. And I have a lot of models that I'm working with solving those three main partial differential equations using a physics-informed neural net. Let me try to get this to skip to the next one. I'll just run with this. We also use a lot of finite element methods in this. So that is another thing, is comparing those two models to each other to producing different spiral candidates. And once we're able to solve these nonlinear parabolic partial differential equations, hopefully we can put them into our model and plot the frequency plots for them as they rotate towards and away the electrodes. So I just want to say thank you again for having me. Sorry for having to deal with my slides not wanting to cooperate with me. Here's a lot of my references here, and I'm going to end on this one plot here that I have, if it will move over. And this is a plot of the complex Ginsburg-Landau equation at t equals 64 seconds. Once it's had time to disperse outwards and interact with the boundary and come backwards, you can see, I guess, kind of reverb back to where it was 56 seconds later. So that is it. And thank you again.
Thank you, James. And just to summarize everything, could you just say again, what is the exact end goal of the project that you're currently working on? And then how does the math ultimately help someone with atrial fibrillation? By way of summarizing the whole thing.
Yeah, definitely. So right now, a cardiologist, the way some cardiologists compare their ablation procedures is like whack-a-mole, that they're essentially ablating in areas and then they reintroduce a heartbeat and then they check with the electrodes again to see if it works or not. And there's people that have their heart all ate up with ablation scars because they're essentially playing whack-a-mole in the heart trying to ablate in these areas. And this is well known. So they're using all types of 3D imaging and medical imaging to trying to find different ways to find these rotors, but the standard method is still with these electrodes. And the electrodes come in many different shapes and forms. Some company like Johnson & Johnson may have a grid shape electrode, and then another company may have a circular shape catheter setup of electrodes. So in our model, if we can show that, hey, here's the spiral that's right on top of these electrodes, and what you may think that the electrode is going away, that the spiral is coming towards this one and moving away from that one, but actually when in fact they're right on top of each other. So hopefully we could implement a model one day soon that we could actually tell the cardiologist this would be the spot that you should ablate in, rather than play whack-a-mole. Yeah, so, and I would say essentially a lot of the math behind this is very rich in obviously numerical analysis and differential equations. There's a huge area of research where you see papers that are pumped out all the time by cardiologists and like mathematicians, which always seemed kind of strange for me to see that, but it's a very, very large field. Yep.
Okay. Any other questions for James?
I have one. I don't know what I'll say here. It's a very, I think out loud in asking my question, but I've been working with a journal for about 21 years, Nonlinear Dynamics in Psychology and Life Sciences. Mm-hmm. And we have articles at least once a year in the journal about, cardiac heart rhythms and all that kind of stuff. Yeah. And frankly, it's way out of my wheelhouse. I mean, the closest thing I have to it is I'm human and have a heart. But where I'm going with this is you actually connected the dot for me, and I don't know if there's a connection or not. But in the nonlinear dynamics world and complexity theory and all that, they've got attractors, what's that called? bifurcation and all that.
Yes.
Is there a meaningful connection, and maybe you just made it obvious, between, you know, quantum dynamics and physics and chaos theory and nonlinear dynamics? I mean, are they
Definitely.
just
Sorry, not trying to cut you off, but I would say yes,
Yeah.
for sure. And a lot of that is actually rooted in the complex Ginsburg-Landau equation as well.
Okay.
That I see a lot of people that do like chaos theory dynamic, like simulations use that equation. I'm definitely not an expert on it. I see these terms like bifurcation come up in my research, and I read a little bit here, and that's kind of one of the really interesting things about the stuff I do is it involves a lot of functional analysis that I have to read up on, a lot of quantum mechanics that I read up on, a lot of Sturm-Liouville operator theory and spectral theory and things like that. So I really enjoy the fact that I get to dab in what I think is literally every area of mathematics, of like numerical analysis, differential equations, probability and statistics. I teach that right now as a PhD student. So it's just really interesting how I've seen the circle of math really come full circle for me. And I do think those topics are all intertwined and related to one another. Yes.
So in the end, how are you going to prove that the model is better, if it is better than what physicians do, you know, by their, I guess, informed intuition or whatever?
Well, the gentleman that we work with that is a cardiologist, his name's Dr. Donald Rubenstein. He's done clinical trials of this, and he's the one that contacted us saying, hey, I've done a clinical trial on this. I'm seeing this in my own eyes. I kind of get the scoop on it. I've ablated at these areas and it's fixed it. And we need, I'm trying to get a paper published. We need a mathematician's perspective to make this mathematically sound. So that's kind of where we stepped in. So I think with his help, with the stuff he's seen in his clinical trials, that this will ultimately show that this, that it will be one step forward into ultimately creating possibly even like a stochastic model of what's happening in the heart and being able to predict this is where you should ablate to disrupt this type of irregular rhythm, right?
I see. So you're trying to distill some expert knowledge into this, but then also establish a foundation so that the mathematics would make it easier for others to
Yes.
perhaps guide their places to try things out.
Correct.
Okay.
Yes, sir. Yes.
Thank you very much.
Thank
All right,
you.
so it's 4:30 now. Any other questions? So if there are no other questions, I just want to thank the presenters once again. This is the end of today's session. Our next session is going to be in July. And I guess we'll let you know. And then we'll join July 18 on Tuesday. We're going to work on the video. We're going to post in a few days and then let you know. Don't forget that there is an office hour in 2 days, Thursday. I'm going to try to get that information to you, as well as the people from the previous 2 sessions this year. With this, thank everybody for coming here today, and hope to see you around.
Yes,
thank you all.
for
Thank
having
you,
me.
Adrian.
Thank you.